the speaker. So hello everybody, welcome in another Information Geometry Machine Learning webinar. Today we have the pleasure of listening to Revant Nayar, who is the principal and CTO at FMI Technologies, quantum-inspired quantitative hedge fund operating in India and the US. He has a background in theoretical physics, specializing in quantum field theories and string theory from Institute of Advanced Studies at Princeton. Nayar also served as a research fellow at NYU Tandon, where he explored novel approaches to option pricing. He is a pioneer in applying, one of the pioneers in applying quantum alternatives to AI in asset management. And he made significant econophysics research collaborations and contribution. He's recognized an innovative leader in quantum and econophysics approaches to asset and risk management. So, okay, Revant, it's a great pleasure to have you today, and the floor is yours. Please say maybe a few words more if I missed something about yourself and the company, and we are looking forward to hearing your talk.
Yeah, thank you so much for that introduction, Pavel. Really look forward to giving this talk, having especially interacted with the professors and students from Stony Brook over the last 3 or so months. So the main the title of this talk, right? It's the physics of endogenous shocks, or how do we characterize or predict endogenous shocks? But sorry, I'm going a bit too fast, I think. Yeah, so I'll just give an introduction first. Let me see. Yeah, this is moving too much time. Okay, so on the surface, this talk is about endogenous extreme events or endogenous shock prediction in markets and in nature. But at a deeper level, I want this talk to be about, what are the guiding principles we can use to select models or quantitative models to describe the world. Modern quants and data scientists have a plethora of models to choose from to describe both natural and social systems. And increasingly so, with the advent of AI, machine learning, and other overly parameterized models. So thus, I think more than new models, there's an increasing need for guiding principles to be able to select models. And as we can see that, as we will see, physics provides such guiding principles, and then we'll obviously apply them to endogenous extreme event prediction. So usually, models in physics are based on 3 principles. We have parsimony, that you should have the fewest possible free parameters describing our system. There should be falsifiability. Your system should be able to be falsified by data from the real world, and your model should be able to explain more than you actually put into it, or explain phenomena that are in essence out of sample. Parsimony is captured very nicely in Einstein's quote, which says, make things as simple as possible, no simpler. So usually what ends up happening is, physicists, we tend to create models that are conceptually complex but computationally simple, whereas often mathematicians tend to create models that are conceptually simple but computationally complex. And nature so far, and as I will argue, markets show a preference for physicist models, essentially. So, for instance, when we observed an anomaly in the orbit of Mercury, there were 2 options. The conceptually simple option was just to add terms by hand in Newtonian gravity to explain the anomaly, right? And that's what most physicists at that time, or mathematicians, did. And the second option was to invent this whole new conceptual machinery of differential geometry to explain gravity as the curvature of space-time, which Einstein did, which, as it turned out, was actually correct, even though conceptually it was much more complex. Similarly, quantum mechanics is very hard to understand. Conceptually, it requires this new framework of Hilbert spaces, quantization, and operators. However, you can compute observables by hand without any compute power. So it's, again, a very successful theory of this sort. And further, both these theories have predictions that went way beyond what the theories were originally intended to explain. So, for instance, with quantum field theory, we predict the top quark and Higgs boson, and then with the general relativity, we predicted black holes and gravitational waves before they were actually observed. So, the correct theories were in general, parsimonious and falsifiable. On the other hand, we have a lot of people who are buy into an AI craze. And if you think about it, AI is, the ultimate, I won't say mathematician's model, but it's a model that's not a physicist model at all. Usually you have millions of free parameters, and it's, hard to feed in stylized facts and symmetries. So, conceptually, it's in a sense simple in that it tries to replicate the human brain, but computationally, it's highly complex. And most physicists, therefore, would not accept a neural network as an acceptable model of reality because it's neither parsimonious nor, in a sense, falsifiable. So, that's just a comment on that. But we're going to examine, a lot of physics-based models and also AI machine learning-based models, and compare them and see how we can use parsimony and falsifiability as guiding principles to select between models, with the specific example of predicting endogenous shocks or endogenous crashes in markets and in nature. So let's see. Let me first define what a bubble is, right? I'm able to actually scroll one at a time. I don't know what's going on here. Shall I just try to do it using the PDF? 1 second. Just give me a second. I'll just try to open this using the PDF. Okay. I guess that's the only option that it seems. Do you see my screen again?
Yes, it works.
Okay. So, essentially, what is the difference between endogenous and exogenous crashes, or endogenous and exogenous shocks? In markets, we usually say that endogenous shocks are caused by the internal dynamics of demand and supply, and exogenous ones are caused by these external news and events. Essentially, it's been shown that both belong to very different dynamical classes, as can be seen from volatility and volume dynamics. in particular, you can look at volume rise and fall before and after shocks, and you see that in shocks that you may characterize as endogenous, there is more or less a symmetric increase and decline of the volume. When both can be modeled by power laws with very similar scaling exponents. But with in the case of exogenous shocks, you find that the volume spikes with the power law with a very large exponent, but it decays much more slowly with a smaller exponent. And in particular, when we are trying to predict shocks or crashes, we usually tend to focus on endogenous shocks because they're the ones that are expected to have certain early warning signals that can indicate the future possibility of such shocks. With exogenous shocks, some people argue that there is some information dissipation and some signals, but usually that's not the case. Yeah. So in a bubble, essentially, the observed price trajectory, deviates from its intrinsic fundamental value of the stock, right? So usually what happens is that when there's a bubble, oh no, when we say bubble, we just mean, in the context of markets, it's just a precursor to an endogenous shock, right? Where the market becomes irrationally exuberant or driven by sentiment, and the price essentially no longer reflects the underlying value of that asset. And then what happens is, when liquidity starts to dry, when banks raise rates, capital inflow stop, there's a panic synchronized selling causing the bubble to pop. And right before a bubble pops, right before the crash happens, the market or your system becomes unstable, kind of like the ruler balanced on the tip of your finger, or also like a droplet, right before it dissociates itself from the faucet and falls down, becomes highly unstable, where even a small perturbation can cause that shock. And this is essentially a symptom of criticality, what we call criticality in physics, which is accompanied by an enhancement of symmetry, and so what ends up happening is that usually in markets, while capital grows exponentially due to compound interest, but because of imitation or herding, there are these positive feedback effects in markets, which essentially result in, instead of P dot proportional to P, it's P dot proportional to P to the alpha, right? And the result of that is that you have these power law growths, or in some sense power law decays, and this process usually becomes unsustainable, and it results in a finite time singularity at some point, resulting in the crash. Okay, so you can see the 2013 Bitcoin bubble here, right? You see a power law increase before the crash, right? It characterizes the bubble. Now we've understood like what a bubble is, and how to essentially what to look for in trying to identify a bubble. Now, in order to predict endogenous crashes or identify these bubbles, we'll consider these following models, which are an increasing order of parsimony. Okay, so first we start with the neural networks, in principle have millions of free parameters. Then we go on to LPPL, which has the famous SORNet log periodic power law model, which has 6 free parameters. Then we go to theory of critical or stochastic phase transitions, which have 4 and 3. And then in the end, we have theory of dynamical phase transitions motivated by group theory, which has 1 free parameter. And as we kind of go in increasing order of parsimony, we will notice, certain features of these models, and we should be critical in how to evaluate them and how to choose between them. So, we can start with the crash prediction using AI. There's been various attempts to use LSTMs and RNNs for crash prediction with mixed results. Tolo, for instance, noted that deep learning and ML models are known for their black box structure, which limits interpretability, which is why they're mostly underutilized or not trusted by economists and policymakers. Moser did a comprehensive analysis where he noted that these models were not able to outperform previously tested models, which in this case were different types of regression models, nonlinear regressions, SG boosts, I think we had SVDs and so on. And then, obviously there are studies that do find neural networks to work for crash prediction, but they do so after trying a whole lot of hyperparameters, such as, number of layers, number of neurons per layer, and a whole lot of different loss functions, etc. So, in a sense, there is, I think, very little evidence that it works without overfitting. And, for instance, Bloomberg has found that more than 95% of AI-based hedge funds have shut down in the last 10 years, usually taken down by large shocks. Usually the problem is that AI and ML cannot deal with small sample sizes and non-stationarity inherent in financial markets, especially near criticality. They're almost too data hungry, almost always overfit as well in the low signal to noise regimes which you see in financial markets. And it usually turns out that with the right neural network, you can predict a crash to happen every single day. You can have, false positives every single day if you want with the right hyperparameters. Therefore, I think we can be justified in putting or characterizing these as not even wrong or unfalsifiable as a category of models. Now, let's move on to model with lesser parameters. So that's the LPPL model, right? And it's a very commonly used model in econophysics. And for instance, Zurich has a financial crisis observatory where Didier Sonnet has basically certain algorithms that operate on the basis of this model and try to predict crashes, right, every month in different indices. So just trying to motivate this class of models, right? Essentially, these are based on a kind of discrete scale invariance, which is the assumption behind these models. It's a weaker form of scale invariance where you have basically invariance under x goes to lambda x, where lambda can take on certain discrete values, right? And in this context, essentially you start with a multi-agent model of investor interactions, which is kind of an icing-like model. So investors can be thought of as spins sitting on a kind of lattice, right? Where they interact locally with each other through interactions Jij, and then globally throughout the system through news or social media, etc., through these interactions H of k, right? And at criticality, what ends up happening is that global effects, the H's, kind of dominate, and investor behavior gets synchronized, and that can result in a crash or an anti-crash as the whole market tends to tilt in a certain direction, right? And so this is kind of the overall context, or this is the framework, the multi-agent framework on which the model is based. In terms of price dynamics, we start with the basic assumption of an SD of this form, with a drift term and a noise term, and DW being just an infinitesimal increment of a Wiener process. But you also add this DJ, which is a discontinuous jump, right, where J equals 0 before a crash and J equals 1 after the crash. And this quantity kappa quantifies the amplitude of the crash once it occurs. And kappa can also be negative, signifying an anti-bubble, which can lead to an anti-crash as well. And essentially, what ends up happening is that you can also define a hazard rate that quantifies the probability of the crash. So you can write an expectation value of DJ and write that as H of t times dt. Now, because of discrete scale invariance, you end up seeing that H of t has to be a power law with a possibly complex critical exponent, right? So essentially, the power law has a real and an imaginary part, and what that means is that once you expand that out and take the real component, is that this H of t essentially can be written down as a power law, and then also cosine component, multiplying the power law, right? Where you have all these free parameters now, and then you feed this hazard rate back into the expectation value of the price change, and you integrate to essentially get this particular expression in terms of the price, or the block price right before the crash, where you have this power law which superimposed by these fluctuations, or these oscillations that keep getting more and more rapid as time goes on and on. And this formula, of course, only works to the critical time, T of C. And this is usually the way these models operate, is that you fit this model to the data by minimizing a least squares residual. And you have essentially 3 linear and 4 nonlinear parameters optimization, and then this can be changed to an optimization of 3 nonlinear and 4 linear parameters. And then, usually it looks something like this, that you want to see these log periodic oscillations before the crash and use them as a signifier of when it's going to happen. But there are several things that are a bit unsavory about this model. First of all, you have usually 6 or 7 free parameters, And as Von Neumann said, with 4 parameters, I can fit an elephant. With 5th, I can make his trunk wiggle. And essentially, putting in a jump is, you can argue, an inelegant and unnatural way to describe an endogenous crash. That's what we want to describe in the first place. So why should we need to put in this jump? But even apart from that, I think having those many free parameters means that log periodic power laws can indeed arise just from random noise or IID Gaussian noise and various other IID noises as well. Essentially, these synthetic time series have been studied, and it has been shown that yes, it can fit various crash and non-crash regimes. Although the likelihood is kind of low, so it's still better than neural networks where you could predict crashes every day. Here, you can't predict them every day, but you can still predict them much more often than they actually happen. So it's a step up, but maybe not all the way there. So let's move on to now even more parsimonious models, right? Which are models that describe crashes as phase transitions, right? And these are really simple. So let's say we start with a generic SD, covering the evolution of our price process. So just examining this SD, right? There are 3 independent ways that we can make this crash without introducing any exogenous jumps or any jump process by hand. So we see that there are 3 kind of knobs here that we can tweak. We want to make a crash. First is we can make the drift term time dependent, keeping the volatility and the noise fixed, which would correspond to a kind of critical phase transition. We can make the volatility time dependent and increasing, sigma, keeping the potential of the drift and the noise fixed, which would correspond to a kind of stochastic phase transition. Or we can evolve the noise term in time, TW, keeping the drift and the volatility fixed, which would correspond to a kind of dynamical phase transition, which arguably does not have an SD or a Lagrangian description, right? So for many reasons, without losing generality, we can write down, we can expand the drift term in the following form with essentially constant, a linear, and a cubic term, which corresponds to a kind of double well potential, the likes of which have been studied by Vishwesha Gottal, Igor Halperin, and others. And we see that essentially what we do is that we increase the term mu with time, and as we increase mu with time, our potential, or this drift inspired potential, goes from the red curve to the blue curve to the purple curve, thereby increasing the probability that the price, which is initially sitting near the minimum on the right, will through stochastic fluctuations shift and tunnel to the minimum on the left, right? So as the potential flattens out, we see that we naively, just visually, we expect to see certain early warning signals of this crash. For instance, we expect to see increasing volatility, right, as the price is allowed to move more and more. We can expect to see increasing negative skewness as the negative moves of the price are now expected to be larger than the positive moves. We also expect to see increasing autocorrelation at lag 1 and decreasing instantaneous frequency, which are both highly correlated, which are also symptoms of critical slowing down. And you can see that by seeing that essentially price that deviates from the minimum of the potential or is perturbed away from the minimum of the potential now takes longer and longer to come back to the center of the potential as it flattens out, which results in these symptoms of critical slowing down before the crash happens. So just visually, one can see these early warning signals, but mathematically also in a linearized approximation, one can check this as well. So, for instance, in this case, in the linear approximation, it's quite simple. we can write down the autocorrelation as an exponential of minus tau divided by mu. You have volatility is being directly proportional to mu, and the power spectrum as having this particular functional dependence on mu. And you see that as mu increases, you have increasing autocorrelation, increasing volatility, and kind of increasing power at lower frequencies, for instance. And you can see that basically mu can also be negative, which will essentially result in the mirror image of this picture. If you flip it along the y-axis, and there you'll have an anti-crash or a large move in the positive direction, and then you'll see similar early warning signals, except you have increasing positive skewness instead of increasing negative skewness, right? So that's the first model where our drift term was changing with time, right? Now we can also have our drift term constant, our potential constant, but our volatility increasing, right? And this has the early warning signals, such as obviously by definition increasing volatility, but you also have increasing negative skewness or positive skewness in case mu is negative, where as the price moves more and more, it can sense out more and more the asymmetry of the potential, but you do not see the other early warning signals of the crash, which is increasing autocorrelation at lag 1 or decreasing instantaneous frequency. And now,
Revant, can I ask you a question?
Yeah.
So you mentioned in the beginning that of course volume has some information about the endogeneity or exogeneity of the crash as well. Here you have the dynamics for the price. Are there models which incorporate the information from the volume and somehow help to estimate those parameters or predict the price dynamics and improve the crash prediction?
I think certainly volume can be taken into consideration. In particular, before endogenous crashes, we do see that power law increase in volume. I do not know, however, if it's a sole predictor of crashes, how many kind of false positives you'd see if you solely rely on that particular measure, and how essentially you would even time the crash if you were to do that, because the volume can have a power law increase for a long period of time. So it's an interesting point. I've not seen it used so much as an early warning signal, though.
To reduce this false positive, concentrate the estimation around volume events.
I think it can certainly be used to reduce false positives, potentially. That's an interesting point.
All right, thanks.
Yeah. So so I mean, we started the critical phase transitions where you change the drift term. Now you have stochastic phase transitions where you change the volatility term. Now the third kind is is the least studied in the literature. I think it's fairly new, and that's basically studying crashes as some kind of dynamical phase transitions, right, where you're changing the noise term itself with time. Think of it as a kind of potentially as a kind of alpha stable distribution with alpha varying over time, right, or some kind of a time varying Hurst exponent. Usually there is no PD or SD description of this kind of dynamics, unless you can make sense of something like time varying fractional derivatives, which are probably very hard to deal with. What we see, if this is the case, is you don't expect to see any of the early warning signals of critical and stochastic phase transitions. But what you do expect to see is increasing anomalous dimensions, which I will define, which are kind of, you can think of as a generalized case of the Hurst and the generalized Hurst exponent. Okay, so basically, before thinking about this, I think it's good to have a short crash course in group theory to motivate this particular discussion. And if some of you don't understand that, that's fine. You can just start after this section ends. But this whole idea essentially relies on the concept of a Lie group, which is a group. There's also a smooth manifold which has a multiplication map and an inversion map, which are smooth, and a certain Lie algebra, right, which is a vector space with a bilinear product essentially, where you write down representations of this Lie algebra on vector spaces, which are basically linear maps that satisfy the fact that these maps on these bilinear products are actually commutation relations. And so we're essentially concerned with the representations of certain Lie algebras in log price time space, because that is the space on which we operate. And we see certain very interesting phenomena if you look at it, which is that for instance, Gaussian markets, which is IID Gaussian, for instance, they satisfy the following symmetries, or they're invented under the following symmetry generators, which are written in the log price time representation as follows, right? For instance, they're invariant under time translations, shifting time back and forth, log price translations, so shifting log price by constant back and forth. They're invariant under boosts, which are kind of like rotating the time on the log price axis relative to one another, and also expansions and dilatations, which together constitute zooming in and zooming out of price and time, where price is zoomed in or out twice as fast as time. And essentially, these symmetries together they close under the action of the Lie algebra, and they form this group called the Schrodinger group, for instance. And then essentially, we can demand that are observable, such as expectation values, are invariant under the actions of these symmetries. But as a crash approaches, or as the normal market regime goes away, it's empirically observed that the market dynamics is now invariant under, instead of x going to lambda x, t going to lambda squared t, it's invariant under x going to lambda x, t going to lambda to the z times t. And this z now starts deviating from 2, and it becomes smaller and smaller and smaller, and you're going towards a value of 1. And when this happens, your boosts and expansions are broken, and the only symmetries which are preserved are your Hamiltonian, which is time translation, log price translation, and this modified kind of scaling symmetry with this exponent z now, right? Usually for the S&P 500, z is actually not 2, it's around 1.7. But what happens is, as a crash, when the crash happens, or before the onset of the crash, right? Like right at the onset of the crash, z goes from its usual value of 1.7 or 2 towards 1, where z equals 1 is is described by another point of enhanced symmetry, which is the conformal group, which we will see. So essentially, the group theory provides this mechanism for interpolating between a normal market regime, or Gaussian market regime, and the crash regime through this group called the Lifshitz group. I'm going from the Schrodinger to the Lifshitz to the conformal group. That's usually the way it's done. And at the time of crash, it's empirically observed that time and price scale uniformly, and your Hurst goes to 1, and it's obviously the 2D conformal group, infinite dimensional group. But the interesting point is that this also corresponds to basically setting volatility to infinity in Gaussian or Black-Scholes dynamics. That's another way to interpolate between the normal regime and the crash. But now what ends up happening is that we have this whole group theoretic machinery, right, to constrain observables, and basically using the price time representations of these symmetries, we can constrain the form of these expectation values. So all we need are time translations and the self-similarity transform, which is the dilatations, and assuming that we can have that the 1 and 2 point expectation values basically satisfy kind of a power law scale, right? Where you have this scaling exponent, which is delta, where delta equals half before the crash and 1 after the crash. It's basically identified as 1 over z, or basically as a kind of Hurst exponent. But our challenge now is to measure the time dynamics of delta. How do we do that? Usually it's identified as a constant, but we essentially promote it to this operator with the dependency on t and tau, right? On time and time lag both, and then we can essentially take the log of both sides, right? And then get this form, and then we can invert this formula to get an expression for this value delta, or the anomalous dimension, in terms of essentially this 2 point product of t and tau, right? So now basically we can get an instantaneous kind of instantaneous snapshot of how this quantity varies with time. And note that this formalism is very general, so we can actually get multifractality here by considering these scaling dimensions of higher power operators at x to the power n, where you get delta to the like delta n's, which are multifractal scaling exponents, where you can also invert them in terms of 2 point expectation values, 1 or 2 point expectation values of these higher power operators, x to the m, x to the n, for instance. And essentially you get multifractality if delta n is not just equal n times delta. And you can also get non-stationarity as before by promoting delta n to be a function of time. And then one can also, in this formalism, break conformality, self-similarity, by introducing a tau dependence on delta, which is outside the scope of the stock. But now that we have a way of measuring these Hurst-like quantities delta and their time evolution, one can see what really happened before these essentially pandemic-induced bubble crashes, right? We had a lot of these pandemic stocks that had high growth in the last couple of years, and then they experienced huge drawdowns afterwards. And there's a whole bunch of them, and so the main punchline here is that the theory of dynamical phase transitions could predict these bubble-induced crashes much better than the early warning signals of critical or stochastic phase transitions, or possibly even LPPL, right? And so we took the top 50 pandemic bubble stocks, and we actually measured the trend in the anomalous dimension using the Kendall tau trend coefficient, when crashes were defined as 10% drawdown. So you see that before the crashes, you see a very strong trend in the anomalous dimension, whereas at other times there is no trend in this anomalous dimension. However, the evidence for other early warning signals is not as clear. You can look at lag1 autocorrelation, instantaneous frequency, and kurtosis. There's almost no trend, and in fact the Kendall trend of skewness is the opposite of what you expect it to be. Like before the crash, you were expecting decreasing skewness. What you have is increasing skewness here. So essentially, it appears that like dynamical phase transitions can probably predict bubble-induced crashes much better than critical or stochastic phase transitions from this preliminary analysis. But of course, I think one should do a more in-depth analysis across maybe a larger data set to make more detailed conclusions. But at least all these models are falsifiable, and they have very clear signals for whether they work or not. So remember, we also talked about how a good theory also predicts things it was not originally intended to explain, right? And One thing, for instance, one stylized fact that we observe is that in the build up to crashes, cross correlations between stocks increase a lot. For instance, the dominant eigenvalues of the correlation matrices usually rise, resulting in more connected correlation networks before our crashes. This was not an input to the model. We never considered cross correlations. However, remarkably, it's predicted by both theory of critical and dynamical phase transitions. So in the critical phase transitions, you see that you can actually derive this via the dominance of the drift term, and essentially the fact that as the drift term starts dominating in one or more stocks, in the multivariate case, it starts dominating in all stocks, causing a concurrent kind of critical slowing down that synchronizes across stocks. Similarly, in the case of dynamical phase transitions, one can see that upon and the expansion of the two-point correlation, basically that the increasing anomalous dimension also causes an increase in the magnitude of the correlations across stocks. So I think that's a sign of a robust theories that it can explain, go beyond what it was originally intended to explain, having out of sample predictions, and clearly, for instance, LPPL and AI ML models, could not have predicted this as another consequence of those theories. So, essentially, just reviewing all the models that we went through, we started the following models in increasing order of parsimony, right? Started with the, let's say, AI, millions of free parameters, which is not even wrong, around falsifiable. And then we went to LPPL, which is, partly falsifiable. Then, critical and stochastic phase transitions, which are falsifiable and mostly false. They have some out of sample prediction. And then dynamical phase transition, group theory, which are falsifiable and hopefully mostly true, with also out of sample prediction. Just a small note on exogenous shocks as well, even though this is not the subject of the current talk. It's something we can briefly touch upon, in that essentially one can model them also with an SD formalism by using a sudden shock or a quench to this SD, essentially this shock can be to the drift term, M, or it can be to the diffusion term, sigma, where the shock can be modeled as a hyperbolic tangent or even approximated by theta function. You see this this exogenous shock, dynamics when essentially the change in your environment is faster than the force that restores the system to its stable state. So there is a critical value of speed above which your shock can be essentially characterized as an exogenous shock. And this is we started using the language of rate-induced tipping in the theory of dynamical systems as well. One can actually use formalism of, for instance, linear response theory to quantify how a shock in a certain variable, say A, can affect another variable B, and the expectation value of the variable B after the shock can be written as the convolution of the forcing term that affects A with a certain kernel function, or which is called kind of a response function, which can also be written as expectation of like B dot A. And we see that if our exogenous shock F is a kind of theta function, we can get essentially these expectation values of a log price and return as and express them in terms of these 2-point expectation values that we can compute. So essentially, physics not only gives us good tools to predict or forecast endogenous shocks, but also quantify the evolution of exogenous shocks after they happen, quantify the aftermath of exogenous shocks after they happen. And the basic conclusion is that physics provides certain guiding principles that help us select models that to describe and predict financial phenomena such as financial crashes, and also other extreme events in nature as well. So we essentially went from potentially 1,000 or a million parameter model to 6 parameter LPPL model to 3 and 1 parameter models, and we saw that as parsimony increase in falsifiability and explainability, and the ability to predict out of sample, and just essentially thank Sasha, Greg, Igor, Pavel, Mihail, Raman for useful discussions, and just bit about FMI tech. It's among the first quantum-inspired quant funds use techniques from physics and engineering to generate alpha in financial markets, very much in the spirit of this talk, and always looking to work with the talented quants, mathematicians, and physicists. Essentially, that's the end of the structured part of the talk. I have some extra stuff in case people want to ask questions. I can, go into more detail on some of the topics.
All right. Thanks, Ravan. This is very interesting. Do we have any questions from the audience? We have some related literature in the chat. For those interested in the topic, I suggest you click on it, because once we finish the meeting, it's gone.
Thank you for the good talk. I have a quick question. Is the group theory providing more insight about the bubble other than what DPT already shown?
Sorry, can you repeat what you said? Can group theory provide more insight than what?
Than the dynamic phase transition model.
Well, so the group theoretic framework basically motivates looking for these dynamical phase transitions. So they're essentially the same. To be able to quantify observables like these 2-point expectation values in dynamical phase transitions, the way you derive them is using the mechanism of group theory, right? So for instance, you assume time translation symmetry. That tells you that this 2-point expectation value, for instance, is a function not of t but only of tau, only of the difference in times, and the scaling symmetry that you also get from group theory tells you that this functional form must be a power law. So group theory is basically helping you behind the scenes in dynamical phase transitions and like getting these expectation values.
I see. Thank you very much.
Hi. I actually had a question about this too. When you promote these deltas to be time dependent, you're explicitly breaking that time invariance symmetry, right?
Yes. So essentially what you do is, when you, So when physicists usually study these systems, they're looking at a kind of a static group that describes the dynamics of a particular dynamical system, right? What we do when we promote delta to be basically introduce time or tau dependencies, that we break this particular symmetry, the particular symmetry group. And we can then have more flexibility in describing not just certain static states of the market, but also the transition from one state to the other, which in this case is the normal market regime to the crash regime. So that's a good observation.
Hi, everyone. It's Olga. Thank you so much for such a wonderful presentation. As always, a pleasure to listen to you speak. Just if you can go back, you mentioned something about I'm sorry if I missed it, neural networks within So do you believe they are, do you think they have their limitations? I just wanted to sort of, because in my mind, from what I understand, is that they are too nonlinear to even apply to finance. They're just way too nonlinear. So nonlinear. So it would not produce any benefit. Let's just put it this way. And I just wanted to see if I missed it, what you had to say, if you agree or disagree.
Yeah, thanks for the comment, Olga. So essentially, I think the problem isn't that they're too nonlinear. The problem is that they're too over parameterized, right? You also have the LPPL model, which is nonlinear, but it has 6 free parameters, and then even all the theories that we discussed today are highly nonlinear. They can be non-perturbatively nonlinear. For instance, even the theory of dynamical phase transitions, you can have very strong nonlinearity, but as long as you have those scaling symmetries, you have only just one parameter that describes them. The problem with neural networks is that you have way too many knobs that you can tweak, way too many parameters. So overfitting is I think the one problem, and the other problem is regime dependence, not being able to adapt to changing regimes because of requiring a huge amount of training data. I think those are I think more the issues here. But yeah, you're right in that usually AI and machine learning are not so useful in prediction problems involving time series or extreme event prediction.
Okay, thank you so much for answering and for the beautiful presentation. Thank you.
Thank you so much.
Hey, I have a quick question. So I was curious, is the motivation for reducing the parameters in the different models down to a 1 parameter model is in order to operate under the assumption that the source of information is from the price process? And then I guess a follow-up question on that would be, if that is the case, how would this framework incorporate information that doesn't come from the price process, perhaps volume or unexpected news that is present in the market?
Right. So, I mean, if you notice, for most of this talk, I'm relying on SD-based formalisms, right? I'm trying to keep it very, very simple and seen based on the SD, how we can make a crash happen of some sort. So in that sense, it usually just describes the price process itself. For volume, maybe you need to write down a different SD, or maybe you can write down an SD for combinations of price and volume, price multiplied by volume or something like that. So that's one idea where you can use that. But I'd say that I think the using volume as a precursor to crashes, it's a more studied field, and in particular, Didier Sonnet and I think Jean-Philippe Bouchot, for instance, they've studied the dynamics of volume before these crashes really well. So I think that's an orthogonal kind of directions. Orthogonal information certainly can be very useful as well to take into account when trying to predict crashes.
Awesome, thanks.
Yeah.
So in this framework of your model, yes, please.
Yeah, if you with the log periodic power laws that you're looking at, I mean, these are actually extremely common in renormalization physics. I got into it from atmospheric turbulence back in the 80s. And the thing that's kind of a hallmark of whether that model can really get much juice out of the log periodic power law is how many octaves, so to speak, does the inertial range have? So in other words, you're going to get these scaling effects as how many periods of the log periodic do you actually get to see in this model? I'm guessing in finance, again, in the atmosphere, you have like 7 decades worth of inertial range. So you can really figure out what that periodic function looks like. But in finance, I'm not thinking that we have 7 decades of dynamic range for any financial variable.
Yeah, that's a great point, right? Just you know, the sheer amount of data you would need to get, you know, even 4 or 5 periods in this can be large. If you're looking at, you know, daily data, for instance, but I think potentially one could look at higher frequency data. I don't know if this has been explored.
I actually have spent 30 years looking at tick data, so I kind of know what that looks like. You are not going to get 10 decades of inertial range in any model anywhere in finance, no matter what. So it's sort of like, to me, log periodic power law is kind of suggestive. One of the things that happens in physics is it's typical that the actual limiting periodic function is nowhere differentiable continuous or something like that. So every period that it gets elaborated to go down the inertial range, it's because it's being stretched out. You see more of the wrinkles in the periodic function, and it doesn't look like the same one. Not because the periodic function is changing in its limit, but because each inertial range doesn't have enough resolution to elaborate the whole function. So I'm thinking if you get like 2 or 3, I mean, how big of a, you want to, even the crash of 29, you know, you didn't give up like 99.99% of the value of the stock market. So, you know, that would only be 4 orders of magnitude. I don't know if the crashes can be big enough to really convince me that a log period.
Andrew, you muted yourself.
Right,
Andrew.
right, yeah.
Oh, when did when I was talking or when I was not talking?
Just 2 seconds ago.
Yeah, I'm actually doing push to talk because I'm on the train and they like to blow the horn sometimes. I'm just saying, I don't think the inertial ranges in finance can ever be big enough, no matter what data you have. I mean, if you look at like operational risk data, you can get shocks that are, you know, 5 orders of magnitude. I suppose if you look at the takedown of FTX, that was a pretty sharp move. But in actual markets, I don't think you get, you know, 4, 5, 6 order of magnitude moves that would really be that many periods for the log periodic model to really sink its teeth into.
Muted again.
Yeah, as soon as I stop talking, I let go of the space
Okay.
bar, so you won't hear the train noise.
Yeah, I think it's a very valid point, right? That you don't often get large moves, you know, with the which can be basically quantified as a crash if you're, you know, quantifying that as let's say, you know, whatever 8 sigma event or something like that. I think a good model, a more robust model, should be able to quantify extreme events which are not necessarily always characterizable as crashes, but, you know, even let's say, you know, 3 or 4 sigma events. And I think the good thing about these models, SDE inspired models, right, is that they're so general, and it's so easy to get, you know, dynamics described by double well potential. You actually see that in actual data so many times. Even when the move is relatively small, you know, you can get 3 or 4% moves of the price, for instance, and also have them have a lot of early warning signals of these, you know, let's say critical phase transitions, stochastic or even, you know, dynamical phase transitions. So I think these certain this whole class of models can probably describe, you know, market moves which are much smaller as well, and hopefully that means that they're much more general as well than ones.
By the way, as far as the double well potential for SDEs go, that's almost the same model as Benzi, Parisi, Volpiani, and the other guy did in 1980 in turbulence. Are you aware of that paper?
I followed a lot of Parisi's work. I didn't necessarily.
This was very early. This is well before the Nobel Prize.
Okay.
But anyways, I put a link to it in the chat in case you want to check it out. It was one of the earliest cases I saw where people had a double well and an SD coupled together at around that same time. It's like 1981, 1982. Yona Lucina was also playing with that stuff.
Yeah, I'll certainly check it out, and I think it's natural that one would see this in fluid dynamics. I know for a fact that in the theory of inflation, cosmological inflation, that is, not financial inflation, people have actually studied a lot of these double well type models, and in particular looked at critical phase transitions as kind of being the precursors to slow roll inflation. Those models look a lot like these SDs with the H being
I think
incredibly
the
large.
cosmic inflation stuff is going to be late 80s, 90s, right? So that's like 10 years after Parisi and Benzi and what was the other guy? Vulpiani and one other guy. Like they kept giving the paper at a couple conferences. I was a student of a climate dynamics turbulence guy, so that's how I know.
Yeah, it's interesting because in fact the dynamical phase transition arguably is even probably a more apt model of turbulence, because there you get multifractality and all these scaling laws very, very naturally, which are not static now, but they're dynamic. So
yeah, it's sort of like where the Yahoo-Orsog theory came from.
Right. Yeah, I think Polyakov had some work in kind of studying turbulence using these formalisms, DPT type formalisms, and since Polyakov, I think there's Yaron Oz and Shiraz Minwala. There's a few.
But the one thing you can say is in turbulence, and even more so in cosmology, you don't run out of inertial range. You have many factors of 10.
Yes, I think that's exactly true. You have probably a much larger inertial range. In finance, you need to essentially specify very narrowly what are the scales across which a particular dynamical theory applies. And usually it's a very constrictive range of scales, because you go to large enough scales, you see a lot of news-induced shocks or a lot of exogenous shocks, and then at very small scales, microstructure noise dominates.
So and the other thing is that at the very small scales, you don't get the diffusion you need. There's no Heisenberg to save you. So at the biggest problem I have is when you had another point in your talk where you said that shocks thermalize the model and generate entropy. Yeah, but at no time do the marginals of these stochastic processes we're actually observing get close to maximum entropy. These are nowhere near exponential families. So we know that finance is under thermalized.
I mean, if we go in finance, how much data do we have? 20, 30 years? I mean, for example, it's not like two major wars, or like it's a curve within a 100-year period, and we cannot go back that much. So there will be limitations to everything, because we just have very limited amount, relatively, 30 years of data. So this is something we'll have to grapple with, I guess. I don't know, a bit unrelated, but just a thought.
I think, we certainly have far lesser data than our counterparts in the natural sciences. But as far as going down to smaller scales is concerned, I think that you can certainly see very interesting dynamics if you model those scales properly. I know that Jack Sarkisian has some great work on these quantum theories of market microstructure, and I think a lot of that can potentially be used to have to be able to study diffusion or entropy creation at smaller scales. But I certainly I don't know enough about that to produce that. But I think it's an interesting possibility.
So when you are estimating those models, you kind of required to already, the crisis to happen, right? But if you want to build an early warning system, how well you can detect the crisis coming if you just see the early stage of the of this transition from with the Hurst exponent. Can you detect this
Yeah. So well,
in the in the early stage?
Yeah. So actually, the increasing anomalous dimension or increasing Hurst are early warning indicators. They're not crash indicators or indicators that a crash has happened. So you see in the build up to the crash, you see the Kendall trend kind of gradually increasing, or positive Kendall trend. So you see the anomalous dimensions very uniformly increasing. And similarly with these other early warning signals, they're certainly what you expect to see before the crashes happen. I mean, once the crash happens, then you don't expect to see the trend increasing. Then you expect to see the anomalous dimension stabilizing at its new value, which is usually 1. Yeah. So
interesting.
Yeah. So all of these are early warning signals. I think what should be more studied is, in order to increase robustness, we can be looking at all the different anomalous dimensions of the higher power operators as well. And then you don't just have Hursts and generalized Hursts. You have this whole family of anomalous dimensions. And I think what you should find is that that if a lot of them are increasing or have a positive trend, you should be fairly certain that you're headed for the crash event.
So let me ask a naive question, maybe. So how does Hurst exponent is related to in discrete time to the fractional differencing operator? So you're saying that when we are entering the crisis, to get the stationarity out of the log prices, you should take lower powers. You don't take the first difference, but some fractional difference. That's what it means. Your PD is then in a fractional power. How does it relate to long memory effects in the price process?
I think certainly if you write down the PD corresponding to it, these processes with these non-trivial Hurst exponents, you will get essentially fractional powers of time, and the exponents of those powers in those PDs or those Lagrangians will be directly related to the Hurst exponent. It's essentially a way of telling you that price and time, or log price and time, are not scaling uniformly anymore, right? They scale with this, like anomalous factor. So you certainly see that there. And for instance, if you can fractionally differentiate these 2-point expectation values also with respect to tau, and then you can get more normal looking scaling exponent here, for instance. But I think when you just look at 2-point expectation values, you don't need to worry usually about the fractional differencing, right? The whole point of this formalism is that you can get an expression for these deltas in terms of these expectation values without doing any of that, any kind of fancy fractional calculus. You can directly, this is a direct observable you can actually measure from the data, and you can quantify its dynamics from the data itself. But yeah, it's related formally to exactly the fractionally differentiated.
All right. Thanks. Any other questions?
I'm a little confused about this 1-point function that you write there that you claim goes like e to the power of delta. I'm a physicist. I'm not a finance person, but as far as I'm aware, in conformal fluid theories, this 1-point function should be 0.
Yeah, so 1-point function is usually 0 unless you have kind of a thermal field theory. And here I'm allowing for non-trivial 1-point function. It's just a choice you have. I think in financial markets is usually not 0. But you're right, in physics, in theories of physics, usually our 1-point functions are 0. Yeah, that's
So what is that sort of capturing in terms of the financial data?
It's capturing the fact that you have essentially a thermal system or a thermal field theory in finance, which usually is not the case in most like QFTs. So even in QFT, right, how do you get usually how you get a non-trivial 1-point function is if you have kind of a thermal average over initial conditions, right, or like you ensemble over initial conditions. So in finance, that's essentially what it's essentially you're assembling your PD or SD over initial conditions. It's certainly far more common, I think, in finance than in theories of physics. I mean, yeah, if you do thermal field theory, you'll see non-trivial 1-point functions as well. Like, for instance, there's a thermal conformal bootstrap where you start from 1-point functions and go up to 6-point function. Yeah. Now they've done it to the 8-point function. But yeah, so that's a good point.
All right. I think if there are no further questions, I would like to thank Revant for a great talk on behalf of the whole audience. And
So much, Pavel. Yeah,
it's very interesting, and it nicely matches with the interest of this group, I'm sure. Next meeting will be after Thanksgiving, so I think it's December 1st or something like that. So don't expect an email from me too soon. I was like to wish you all